Hi, my name is dr. Ahmath. In this video lecture, we are going to discuss about how to solve the least squares problem using the matrices, using the tools of linear algebra. So in our previous video, we discussed how we can solve this problem by finding the best line which is going to fit to the 3 points, for example, using the tools of calculus. So what we did is we found the 3 points on this line, we found the distances between the 3 points with the given data points, and we basically constructed the cost functional, which is basically the sum of all of these distances, and we minimize this cost functional by taking the partial derivatives of this functional with respect to the k and c and equalizing them to the 0. So we are going to solve the same problem. We would like to find this line, essentially the line which is described with the k and c constants, here, using the matrices. So let's learn how to do this. So before we do this, we are going to again start with a simplified version of the problem. So let's say you are given 2 points and you would like to construct a line through these 2 points. Okay? So the equation of any line is going to be given as a y is equal to the kx plus c. So since these 2 points are on the line, it means that if I substitute the coordinates of these 2 points to the line, they have to be substituted. So essentially, if I substitute the coordinates of the first line to this equation, it's going to be equal to 0 is equal to 5k plus c. And if I substitute the coordinates of the second point, it's going to be 3 is equal to the 0 times the k plus c. Okay, so it is going to be a system of linear equations with the 2 equations and 2 unknowns, k and c, and we can find this by solving the system. And again, so if I substitute the first point, it's going to be the first system like this. If I substitute the coordinates of the second point into here, I'm going to get the second system. So I would like to solve the system using the matrix equation. So I'm just going to copy the coefficients before k and c into this matrix. I'm going to call this matrix as the A matrix, okay? And the unknowns are going to be copied to this vector x, which is going to be the unknown vector x. And the right-hand side part vector is going to be constructed using these numbers from the right-hand side, so which is going to be denoted as the b. Okay, so solving solving this matrix equation is going to be equivalent to the solving of the system. And I'm going to solve this by just looking to the second equation, for example. If you look to the second equation, it's clear that it's written c is equal to the 3. Right, so if you substitute this to the first equation, it's going to be 5k plus 1 times the c, which is 3, should be equal to the 0. From here, we can obtain that the k is equal to the minus 3 over 5. So essentially, our line has the equation kx is equal plus c, where the k is minus 3 over 5x plus 3. Okay, so in general, you need to solve the system of linear equations by creating the augmented matrices, and you can apply, for example, the Gauss-Jordan elimination in order to solve this kind of system of linear equations. But this was the simplified version. So in order to just show you how you can find the equation of a line through the 2 points by using the matrices. Okay. Now let's assume we have got the third point and we would like to create a line through this point. Obviously, this line doesn't exist. And what we want is we would like to create a line which would fit to this data points in the best way. Okay. And what do I mean by in the best way? So it would express all of these data points in the best way. And we have to play with the constants k and c of this line, the parameters of this line, where the k is going to be called as the slope of this line, which is going to control the slope of this line. So it is how much rotated this line. And the c is going to control the height of this line, essentially. So what is the height of this line? So by just taking the different values for the k and c, we can control the slope of this line and the height of this line. So we can choose the best line. Okay. So from the linear algebra perspective, what we want is we would assume that hey, all of the 3 points are on this line. where the equation of this line is equal to the y is equal to the kx plus c. So if you assume that all of these points on this line, it means that if I substitute the coordinates of this point into here, it should be satisfied, and I need to get this equation, right? So the x should be substituted with instead of x, and so 5 should be substituted instead of x, and 0 should be substituted instead of y. If I substitute the coordinates of the second point here, I need to get the second equation. And if I substitute the coordinates of the third point to here, we need to get the third equation. So this is what we did when we found the equation of a line through the 2 points, right? We substitute the coordinates into the equation, we derive the system, and solved it. So this is what we're doing now as well. So we've got 3 equations now, and we are going to construct a system of linear equations. So this is going to be our system of linear equations with 3 equations and 2 unknowns, okay? And I'm going to write this down in a matrix form by just rearranging the vectors. So it is going to be written as in the form of ax is equal to the b, okay? Where the x is going to be the unknown vector, which is going to contain the parameters of that regression line, of that line, which is going to fit in the best way to our data points. The problem is we know that the system does not have any solution, right? So this line simply doesn't exist. So I would like to look a little bit more deeper into the subspaces of the matrices in order to try to understand what does it mean that the matrix equation does not have the solution. So if you remember, any matrix equation, when we write this down in the form of ax is equal to the b, and solving any matrix equation basically means figuring out a proper linear combination of the columns of the matrix A, which would give us the vector B. So essentially, you are given the matrix A, it has some certain columns, okay? You need to combine them using the rows essentially of this vector x, okay? And you need to find a proper combination of the columns of the A, which would give you exactly the B, okay? And when the system does not have the solution, it would mean that this B is not in the space. Well, when the matrix has 2 columns, as in our case, the column space of the matrix is going to be the plane. So all of the vectors along this plane can be obtained as a linear combination of the columns of this matrix A. But if the vector B is outside the plane, then obviously no combination of the columns is going to give you this B. Now the problem is we don't want to give up, and we still would like to solve this problem. I would like to approximately solve this problem. So what would be the closest vector to this vector B along this plane? What would be the vector along this plane, on this plane, which is really close to this B, the closest one? So obviously it is going to be obtained when I make the orthogonal projection of this B onto this plane, right? So we are going to make the orthogonal projection onto this plane, and this vector P, the projection of this B onto the column space, is going to be the closest possible vector to the B, which is still on the plane. It means that we can find this. So we've learned about how to find this vector actually. So there's a long formula which enables us to calculate this, evaluate this vector. And I would like to show you a couple of tricks where you can find this vector without learning this kind of formula. So what you need to do essentially, so you need to write the system of linear equations, ax is equal to the b, or the matrix equation ax is equal to the b in this form. You just multiply A transpose from both of the parts. So now we are going to solve this system. Instead of solving ax is equal to the b, we're going to solve this. A transpose to the A, which is going to be one matrix, times the x is equal to the A transpose to the B. So obviously this x is going to be different than the x on the ax is equal to the b, right? So that's why we are going to denote this as the x hat, which would mean the solution for the least square problem or the approximation problem. Okay, so this x hat is going to have this parameters of that line k and c, okay, the optimal ones. So solving this system, so this is going to be considered as one matrix times another vector is equal to the third vector. is going to be considered as the matrix equation. And by solving this, we can figure out the best parameters. So this is actually what we want. So we would like to solve now the system in order to our example, in order to solve the line. So the parameters of the line. So in order to solve the system, you can just put this matrix into the right, sorry, by multiplying both of the parts to the inverse of this matrix. And the projection vector actually is just a multiplication of the A into this X hat. Okay, so it's a specific combination of the columns of the A, where the constants, the coefficients of that linear combination is going to be the components of this vector X hat. So, well, essentially, if you just substitute the formula of the X hat, which we just found, to here, you're going to get this formula, which is the formula of the projection vector. Okay, so this is the long formula. So for example, personally, I don't remember this, but I always can get this formula from this equation AX is equal to B by just multiplying this equation from both of the parts to the A transpose. So now let's find this vector X hat. Let's solve the system. So in order to do this, we need to calculate A transpose to the A and A transpose to the B. So we're given these matrices A and B in the following way. So let's do the calculations. If we multiply the A transpose to the A, what kind of matrix we are going to have? So the A transpose is going to be 0, 1, 5, 1, 1, 1. It is multiplied to the A, which is like 0, 5, 1, 1, 1, 1. Well, the matrix, the resulting matrix is going to be a 2 by 2 matrix. If you multiply the first row to the first column here, it's going to be equal to the 26. The first row to the second column, it's going to be 6. The second row to the first column is going to be equal to the 6. The second row to the second column is going to be equal to the 3. Well, at the same time, A transpose to the B is going to be equal to 0, 5, 1, 1, 1, 1 times to the 3, 0, minus 2. So it should be a vector with the 2 rows. So we can obtain the first row by just multiplying the first row into the first column. It's going to be equal to the minus 2. And if we multiply the second row to the first column, it's going to be equal to the 3 minus 2, which is plus 1. Well, I'm just going to substitute this to here instead of this matrix. And this vector is going to be substituted with the new vector. And we're going to obtain the new system of linear equations, or the new matrix equation. And we're going to solve this. Okay, so we've got this matrix times the z, k hat and c hat is equal to this vector. So in order to solve this, we need to put this matrix into the augmented matrix. It is going to be 26, 6 minus 2, 6, 3, and 1. We need to, for example, eliminate the 6, and we can do this by multiplying the first row to the minus 6 over 26 and adding this to the second row. So it's going to be a little bit ugly, but we still can do this. So the procedures are in the following way. So we have to eliminate that 6. So we multiply the first row, all of the entries on the first row, to the minus 6 over 26. If we multiply 26 to this, we are going to get minus 6. If you add this to the plus 6, it's going to be 0. So it's going to be 26, 6, and minus 2. So this component here is going to be simply equal to the 0. So the second component here, so I have to add 3 to this number multiplied to the 6, right? Which is going to be 3 minus 36 divided to the 26, right? And at the same time, we have to multiply minus 2 to this number and add this to the 1. It's going to be 1 plus 12 over 26. Okay, there are lots of numbers here, right? But we still can do this. So let's look to the second equation, second row. It is actually 78 minus 78 minus 36 divided to the 26 times to the c, because do you remember this vector, or this vector, has the two unknowns, x hat, so k hat, and c hat. So we have to find this c hat. So the c hat here is going to be equal to, so 78 minus, so we've got the 78 by multiplying 3 to the 26, right? Minus 36 divided to the 26 times the c hat is equal to 26 plus 1 is going to be equal to the 26 plus 12 it's 26 times 1 is going to be 26 plus 12 is going to be 38 divided to the 26. So from here we obtained that the c hat is equal to, so this is 42 if it goes to the right, so we can cancel this 26 and 26. It's going to be 38 over 42, or simply 19 over 21. Okay, so we are going to substitute, for example, 38 over 38 over 42 to the first equation, or to the first equation here, and obtain the k from there. So it's going to be 26 times the k is equal to minus 2 minus 6 times the c hat, right? So it's going to be 38 over 42. So this 6 and this 42 is going to be canceled out. It's going to be 7, right? So this is going to be minus 2 times the 7, minus 14, minus 38 divided to the 42. Okay, so minus 14 minus 38, it's going to be equal to the 52, by the way. Okay, so from here we obtain that the k is equal to the minus 52 over 42 times the 1 over 26, which is minus 2 over not 42 anymore, it should be 7, sorry. It should be 7 there. So minus 2 over 7. Okay, that's the value of the k hat, and this is the value of the c hat. They are going to be the solutions of our system. Okay, so they are going to be the parameters of that line. So this is the k hat, c hat. It is equal to the minus 0.28 if we write this in the decimal form, and the 19 over 21 is going to be roughly 0.9 if you write this in the decimal form. So we solve this problem. Instead of solving ax is equal to the b, we solve this one. So obviously this x hat is different than this x. They are not the same, but it's going to be the best, the closest vector. So this a times to the x hat is going to give you really close to this vector b. Okay, so now if I just put this line onto the graph, we would get this kind of line. So this is essentially how we can solve the least square problem using the matrices, the least square using the matrices, and by applying so-called projection vectors. So I hope that this video was helpful for you. Thank you very much.